evening, everyone. So, welcome to the iCANX talks, Connecting the World and Universe. My name is Paolo Samori. I'm the moderator of the today lecture. And so from the University of Strasbourg. And actually today we have an amazing speaker and a set of colleagues that are in the panel. So the speaker is Professor Nazario Martín from Madrid. And actually we have Professor Martín is a professor of organic chemistry at the UCM and vice director of the India Nanoscience Institute. He has an honoris causa laureate doctorate at Havana University, at Castilla-La Mancha University. Is member of the Royal Academy of Science of Spain and Royal Academy of Doctors of Spain. His research interests are very broad. They are focused on supramolecular and molecular carbon-based nanostructure in the context of chirality, of electron transfer, of biomedical and photovoltaic application. He published over 600 peer-reviewed papers and supervised as many as 50 PhD theses. So he was editor of Journal Materials Chemistry and also he both ABC. He held the presidency of the Confederation of the Science and Society of Spain and the Spanish Royal Society of Chemistry. He actually held a ERC, European Research Council advanced grant on carbon, and is distinguished for a very long list of awards. Among them, for example, is a gold medal and a research award of the Chemical Society in Spain. Is the Jaime Award, research award, basic research award in 2012. A Miguel Catalan Award of the Chemical Society. Is also Alexander von Humboldt Award, Richard Small Award in 2013. He gave the UCAMS lecture, and recently he has been awarded also a synergy grant from ERC. So this is a very big project, very prestigious, that is called Tomato. And also he has a number of national awards in chemistry. So with this, I want to cut our introduction short because we have to spend most of our time to hear this fantastic chemistry that will be introduced by Professor Martín. Nazario, the floor is yours.
Thank you so much, Paolo. Thank you so much indeed. And now let me go to my presentation here. Can you see
it? Yes, we can see it.
Okay, perfect.
It's okay then? Yeah? Okay, first of all, yeah, thank you. First of all, I'd like to thank to the organizers, in particular Alice, but also to Paolo, not only for the invitation, but also for acting as a moderator, and thank you for your kind introduction. And also, I want to extend my gratitude to my colleague and friend, Irena Stará from Czech Republic, and she, together with Professor Junsi Liu, are acting as panelists. And the most difficult person to deal is our challenger. The name is the PhD student Shatin Dai. And I'm very, very, all of you, welcome, and I appreciate your presence here to go ahead with this important event. So I would like to start before introducing my topic for today. Let me tell you which are some of the research topics we are currently developing in the both institutions where I'm working, in the Complutense University and also in the Nanoscience Institute in Madrid. So related with this topic, with graphene, we have carried out along these last years, well, not only the covalent chemistry, but also non-covalent chemistry involving graphene, usually with the presence of photo and electroactive molecules. And also in collaboration with physicists at the India Nanoscience Institute, we have carried out what we could consider a kind of organic electronics, where, for instance, you can see here how the graphene deposited on a metal surface and the electron acceptor molecules is able to form, for instance, just a kind of ferromagnetic behavior. Or a very successful project that we have developed along the last few years devoted to on-surface synthesis, if possible. The last 3 or 4 slides today, I would like to show you some of these wonderful systems made of carbon. So also fundamental questions like chirality in graphene quantum dots have been addressed in our group. And not only the fundamental question, but also applications, for instance, biomedical applications involving a variety of carbon nanostructures, usually decorated with carbohydrate. These glycofullerenes, for instance, have been mostly devoted to emergent viruses, including the SARS-2 COVID. Also, I want to point out this aspect because supramolecular, this concave-convex interaction is a different or singular supramolecular interaction by its own right. And here we have devoted also some studies. And just to conclude this picture, let me show you something related with carbon nanodots. These are not properly graphitized structures, but at the end, they exhibit interesting properties that has been enhanced, these properties together by mixing these materials with photo and electroactive species as well. So today I would like to focus specifically in this topic, chiral graphene quantum dots. And in this regard, what I would like to say before starting is to pay your attention to this paper. Was a special issue devoted to advanced molecular nanocarbons. It was come out in 2019, and within the chapter, which appeared with this periodic table, because it was the international year for the periodic table, but of course, remarking the singularity of the carbon atom. But in this case, in this special issue, we dedicated a review article to chiral molecular carbon nanostructure. Some of these molecules will appear now in my presentation. So on the top, you have the title for my presentation today, and the outline is shown here, mostly devoted to synthesis, how to introduce chiral elements in the nanographenes. The first one, the easiest one, would be just to add chiral elements. But also synthetically much more demanding would be to form inherently chiral nanographenes. This means introducing curvature or helicoidal moieties within the system. Related with the reactivity, I would like to focus specifically in 2 aspects: the supramolecular ensemble, the formation of supramolecular complexes, and also in the redox reaction of nanographenes with mostly alkaline metals. This has been mostly devoted in collaboration with Marina Petrokina, as I will show you later on. And then to conclude with some photophysical and chiroptical properties that these carbon-based structures are able to exhibit in a remarkable manner. So altogether, hopefully will provide you general information about how to obtain these materials and how to study what properties they have. So let's go. But let me just to tell you that as it was pointed out by in my introduction, we had a previous advanced grant, ERC grant, where it was chiral allotropes of carbon. So in this grant, we wanted to use or to synthesize chiral fullerenes at will, probably by using the most powerful tool in organic synthesis, which is asymmetric catalysis. So in a few words, if you take the right fullerene, the right 1,3 dipole, and you put it together with the appropriate catalyst, you put all together in this shaker, and after shaking, you get a variety of cocktails, like you can see here, fullerene cocktails, where not only C60, but other larger fullerene like C70 or endohedral fullerenes have been covalently connected to different organic addends, for instance, carbocyclic systems or heterocyclic systems, which, however, were decorated for the first time with one or two stereogenic centers. These systems, these stereogenic centers, chiral carbon atoms, are absolutely controlled all the time, and we were able to use these materials together with different metals, active metal like iridium, rhodium, or ruthenium. Here you have an example with iridium, to form these much more complex structures, which at the end have 4 stereogenic centers, and these systems were tested in our group as catalysts in a variety of hydrogen transfer reactions in a very successful manner. This was one of the first examples where fullerene derivatives were used for catalytic purposes. Mostly, we studied the reduction of ketones to alcohol and also alkylation of amines from alcohols as well. So this was the experience that started with this Nature chemistry paper in 2009. So let's go to graphene then. What about graphene? Everybody recognizes graphene. The definition for those students is 2-layer carbon atoms, which are arranged in this honeycomb lattice and having one atom thickness. In addition, everybody here or recognize that the graphene has a variety of very important outstanding properties. But since this is very well known, today I will not focus specifically on the outstanding properties. On the contrary, I want to put put your attention in those lacking properties in graphene. Why? Simply because this limits the potential applications of this material. What kind of properties we are referring? Well, the first one is this one, which is the fluorescent, in particular photoluminescent, because of the energy, the Fermi energy level, which is located in this crossover point. It is graphene has a 0 optical band gap, and therefore it lacks some optoelectronic properties, in particular fluorescence, for instance. But in contrast to graphene, if you take just a piece of graphene, mostly it can be like in this example I will show you later on, but this is a flake of graphene or a piece of graphene. Because of the electronic confinement, that means that the electrons are localized in a very small space, appear new energy levels, and as a consequence, you can see that these materials, in contrast to pristine graphene, they exhibit, like in this case, a vivid yellow color, which is stemming from the fluorescent or photoluminescent properties of this material. So this is the first thing. Small pieces provide properties that pristine graphene doesn't have. And in addition, what about chirality? Well, if you have a piece of graphene is formed exclusively by hexagonal rings, and therefore there is no possibility of chirality. In our case, we feel that despite the many advantages of graphene, it lacks chirality, and therefore we consider is missing a further dimension of control. So what can we do to introduce chirality in this piece of graphene? There are 2 options. The first one would be just to add a chiral element. You can, by these red lines, these elements, these chiral centers could be just covalently or non-covalently connected to graphene. This is, let's say, the simplest way to do it. But the second one would be much more synthetically much more demanding, is just to form inherently chiral graphenes or nanographenes. Okay. In this case, the chirality is stemming from topology or defects. Okay. So, for instance, curvature, the presence of helicenes, or whatever. I will show you some examples in the next slides. So let's go for the first approach, which is by adding chiral elements. This is the example we reported in 2016 in our group by using what is called a top-down approach. So we obtained these synthetic chiral nanographenes by taking pristine graphene. If you undergo this graphene to the Hammett method, that means that you are oxidizing the graphene into small pieces of graphene or flakes of graphene, which are decorated at the periphery with carboxylic groups. Yeah, the next step would be to carry out the reaction, the esterification reaction, in this case with this 2-phenylpropanol, both R and S enantiomers. At the end of the day, you have your systems here, which are chiral, R and S. And yeah, in this case, you can see that because of the electron confinement, these systems are able to exhibit also photoluminescent properties, in this particular case, fluorescence. Just a few weeks after our paper, Kotov reported in ACS Nano a similar paper. It was actually a flake of graphene. Of course, this has been also similarly to our case. It needs the carboxylic groups in the periphery, but the strategy was pretty much the same, because it was reacted with amino acid, both L and D enantiomers, just to get the corresponding amido derivatives. Here is written this like a mirror image. This is simply impossible. So it's quasi-mirror images, because you don't have any control on the size and shape of these systems, because we are using a top-down approach. So this control, that means these are the two first, to the best of our knowledge, these are the first chiral graphene quantum dots reported in literature. But, well, they are beautiful examples by gathering chirality and nanographenes together. But there is not much control on the structures in terms of size and shape. However, these are interesting because well, what I mean is that this is one approach, and let me show you just one example we reported last year, in which you can see that by forming this supramolecular assembly of functionalized nanographenes, these nanographenes were obtained by a top-down approach. That means that the carboxylic groups were reacted with just forming with an amino group, amino acid group. And in this case, you have a chiral center here. And because of the presence of the amido groups, you have supramolecular hydrogen bonding in between them. And also these pyrene units provide a pi-pi stacking interaction. Just by taking these systems where, again, I remind you that there is no, here is the same, but there is no control on these systems, but they are able to form supramolecular ensembles which exhibit chirality. Just to prove this, I will not go very much into detail, but you can see that in addition to the fluorescence they exhibit, both supramolecularly or covalently connected, they exhibit also the dichroic signal. It is a positive and negative cotton effect. Of course, that this is not exactly a mirror image, but it couldn't be, because you don't have control on the size and shape of the central core. So this is a beautiful example that you can get that can be obtained by using this top-down approach. Professor Aino, for instance, has many excellent papers on this topic by using this approach, just to give a name. Okay, so let's go to the structures. I want to show you today. These are the second approach. I mean the synthesis, the top-down approach. The bottom-up approach by using standard synthetic methodology. In this case, you are seeing a few of the molecules we have synthesized in our group. Let me tell you that what you are seeing here are not cartoon, they are X-ray crystal structures, okay? And there are some of them I will dedicate my presentation today, like this new family of bilayer nanographenes, which are chiral because of the helicene moiety here, or any other system like this, where you can see the helicene moiety in this case. These compounds exhibit chiroptical properties, But because of the electron confinement I showed you before, these molecules are also photoluminescent, so they have fluorescent features like these colors you are seeing here in this picture. So today I would like to focus specifically on these molecules that we published at the beginning, the synthetic method a few years ago, but has been studied much more into detail very recently. Well, today I will not mention anything about this molecule is here, but let me tell you at least that this is another bilayer, but the molecule has 5 different stereogenic centers. All of them have been obtained in a controlled manner, and this is the first enantiomerically pure compound has been obtained synthetically. What I mean is that in this case, we obtain, by using asymmetric catalysis, the pure enantiomers for the first time in the literature. Okay, so any of these enantiomers in these molecules, they have to be separated by HPLC, as I will show you, but not in this case for the first time. So let's start, and let me go to the first molecules, starting with something that everybody recognizes. These are polycyclic aromatic hydrocarbons. Always that you have these kind of systems which are formed exclusively by benzene ring, hexagonal rings. Typically, you get a planar system. But be careful with this, because let me show you that this is there are some exceptions, and these exceptions are really fantastic because they provide topologically provide defects that, for instance, in the case of the 6 helicene, because of the steric hindrance, this molecule is not planar anymore. And or for instance, the cycloparaphenylines, like in this example, where there is a highly strained system, and therefore they exhibit this curvature. But there are other molecules. Simpler molecule like 7-circuline, which exhibit a non-planar geometry, or this is a negative curvature. I don't have time for going into detail, but Professor Kim Miao have a wonderful paper where you can go to this topic. This is a coranulin, very well-known molecule, highly extensively studied, and this has a positive curvature because the pentagon is smaller than the hexagon. And but if you put attention here, you see that pentagon is synonymous of a loss of planarity or the presence of curvature. If you increase the number of pentagons, the larger number you can get together is 12. And 12 is exactly what you obtain with the molecule of fullerene C60. It has 12 5-member rings. C60 has, in addition, 20 hexagons. But any molecule having in between 1 pentagon and 12, it is the molecule that we call, in a general manner, ball-shaped molecules, or you can also use the nickname, which is the buckyballs. Okay. So let's start with the second approach to form chiral nanographenes, which is synthetically much more demanding. Is what I mentioned as inherently chiral systems. So in this case, the objective was just to put together, the inspiration was to connect coranulin, which has curvature, together with the hexa-benzocoronenes, which is planar. Actually, hexa-benzocoronenes is considered the smaller nanographene. It has a diameter roughly around 1 nanometer. And the strategy is just to to introduce the hexa-benzocoronene in this polyphenylene, it would be hexa-aryl benzene, where one of the aryl groups has been replaced by the coranulin. Well, this molecule is simple to do, but we started our study on it because, in principle, you can recognize that there are 2 options for cyclization: the formation of this carbon-carbon bond forming a 6-member ring, or this one. but in this case, you are forming a 7-member ring. So we decided to study this, in principle, simple problem. So the person who did it was Chus Fernandez. He is a postdoc in the group. He's one of the expert people in our group in this topic. And just by using the coranulin was provided by my friend Jai Siegel, and just by carrying out typical and standard synthetic pathways, bromination, and further introduction of the alkyne by palladium catalyzed cross-coupling sonogal cross-coupling reaction, you get this compound followed by 4+2 cycle addition reaction. This is a Diels-Alder reaction by removing carbon monoxide under microwave conditions, and you get this molecule was what we wanted to do. The presence of tertiary butching group is just to increase the solubility of the molecule. The last step was graphitization, so that means to form these bonds, and it was used by, typically, it is the salt reaction that is carried out by using iron trichloride in a big excess in nitromethane, dichloromethane, room temperature for a few hours. In our case, instead of having the expected compound, we could see that 2 new compounds were formed. And if you consider the molecular weight of the starting material, the loss of 10 and 12 hydrogens occurred. So we decided to study this reaction in a much more carefully manner. And Chus decided, he carried out the reaction now starting at minus 50 degrees in just 15 minutes. The salt reaction was performed very efficiently. By the way, the salt reaction typically is not carried out at very low temperature, but we started doing this, and they performed pretty well indeed. So in this case, we obtained these 5 new carbon-carbon bonds and formation as was expected of the 6-member ring. So and that is 5 carbon-carbon bonds, the loss of 10 hydrogen atoms. So we try to increase the conditions just simply playing with the temperature. We increase 130 degrees in 15 minutes. We obtain not only the 6, but also the 7-member ring. But together with something that was not completely unexpected, because you have a lot of chloride chloride anions, and a chlorine atom was introduced in our compound. Well, we didn't want to have the chlorine atom, so we looked for different experimental conditions, and as a reagent, we used DDQ as an oxidant reagent in triflic acid, dichloromethane, 0 degree, 15 minutes, and eventually the expected molecule with the 6 and 7-member ring was formed in roughly 50% yield. So it could be considered that compound 6 is an intermediate in the synthesis of 8, and therefore we undergo 6 to the same conditions to obtain 8. So 6 was reacted with DDQ under the same conditions, and we obtain compound 8 in a quantitative manner. So what we have is a battery, is a family of compounds having this helicene structure. So this has a positive curvature with a helicene, and therefore it is obtained as a racemate because we have the 2 enantiomers of the helicene, and we have compound 8 with a positive and negative curvature. Here there is not helicene anymore, and therefore the molecule is not chiral. But we have the formation of the 6 and 7-member ring. I have to say that in any case, the formation of the 7-member ring was observed as the only closure, ring closure. So it's always formation of 6-member and 7-member. Okay, since this paper was published a few years ago, I will not go into detail the characterization, simply to test, to show you that the molecule is fine. The X-ray crystal structure of the 3 molecules was obtained. Basically, 2 kinds of molecules, the helicene, and therefore chiral, or although obtained as a racemate, and this 7-member ring, which provide different properties to these materials, as I will show you later on. And the first property we wanted to study was because of the curvature of this molecule with the 7-member ring. The idea was just to see how skillful was this molecule to form complexation with convex surfaces like those of fullerene. In this case, well, this is a paper was published last year, and sorry, it was the proton NMR studies were carried out here, and well, these studies were carried out in an NMR tube just by putting 5 × 10⁻⁴ molar in the deuterated toluene solution, and then it was added in a sequential manner a solution of C60 with a concentration that typically is at least 1 order of magnitude or roughly 1 order of magnitude higher, so 10⁻³ molar. And under this condition, you can see that there are two hydrogen atoms, A and D, in which you observe are downfield shifted, okay, as you can follow in the titration experiment. And on the other hand, there are another two in red, B and C, which are upfield shifted. Well, we determine the position of these hydrogens by rather complex 2D NMR experiments. But anyway, this is the experimental observation. Theoretical calculations were carried out, and here you can see the optimized structures and also showing the interaction energies of this, which are the most stable conformers, which are those shown in the screen, on the screen. And well, although this is a little bit, the value is a little bit overestimated, they fit pretty well in the sense that the complexation here is involving two molecules, two nanographenes, is roughly the double to that obtained for this one. The binding constants, by the way, resulted to be very similar in all cases, and is roughly in around 2 or 3 10⁻³ molar -1. It is interesting to note that just when 1.5 equivalents of C60 were added, all the three complexes, the thick complexes were formed. So, and this is what you can see here. And of course, that here these are the most favorable. So the energy has been optimized, the energy, but there are other possibilities because for the stoichiometry 1:1, there is only two cases that the concave convex surfaces are interacting, or the convex surface of fullerene with the planar surface. But you can see that this is not so favorable. So concave convex interaction, as I mentioned at the beginning of my presentation, is quite singular interaction. For the nanographene 1 C62, there is only one possibility, which is the calculated one. But if you take two nanographenes and one C60, with this stoichiometry 2:1, there are several possibilities. But again, this is a much more stable. So this was what we studied. These studies were carried out by my colleague and friend Miquel Solà in Girona University. Okay, he also carried out the non-covalent interactions, and he could determine these surfaces, which are quite interesting to see that these the interactions in these green areas are not due or focus on atoms, but are related with surfaces, with areas where the interaction is much more favorable. For the three stoichiometries are shown here, and he could carry out something which is not so simple to do, which is the energy decomposition analysis. This allows you to determine which is the term which is much more important within the supramolecular interaction. And in these examples, as it could be expected, the dispersion term, I mean the van der Waals interaction, resulted to be the most significant interaction, supramolecular interaction. But also the electrostatic term, with almost 1/3, in between 26 to 29%, was quite significant. This in some way is talking about the possibility of having a kind of donor and a kind of acceptor. So the electrostatic term could also play an interesting role. So, and just related with this aspect, in collaboration with Professor Dirk Guldi from Erlangen University in Germany, he could, actually, he carried out the time resolved transient absorption spectroscopy at the nanosecond time scale. And it could be observed that in the less polar chlorobenzene as a solvent, you see that this is in blue. You can observe here a signal at around 750 nanometers, which corresponds to the triplet excited state of C60, as it is shown here. Okay, but if you so that means that there is a kind of energy transfer in this system. But in using a much more polar solvent like benzonitrile, then the triplet excited state disappears, is not here longer anymore. And instead, you can see in blue that in this region, which is an artifact of the equipment, but is increasing, there is a maximum around 1080 nanometers, which is a typical signature for the radical anion of C16. Okay, so this was a proof that there is a kind of photoinduced electron transfer process that could be visualized or figure out that light irradiation promotes the electron transfer from the donor to the acceptor, giving rise to this radical ion pair or charge separated state. What I want to bring to your attention is that, yeah, we are dealing with a donor and acceptor, which are constituted exclusively by carbon atoms, of course, with the hydrogen. But what I mean is that the donor and acceptor character is contained in sp2 carbon atoms. And this is quite remarkable. Okay, so let's go to another property of this family of compounds. In this case, it was not the seven-member ring, because the seven-member ring was much more interesting for the pi-pi interaction, the supramolecular complexation. In this case, it was tested by Marina Petruchina from University at Albany. And this was the nanographene, which was able to provide crystals. So this is a quite singular experiment. I would say that only Marina is able to do it in Albany. And he, I would say, is the most expert people in the world in this topic. So she put the nanographene in THF, and it was was added sodium, and in this case it was obtained this compound in which you see that there is a dianion of the nanographene. By means of the UV visible spectroscopy, it could follow. She could follow the reaction, and you can observe here that after 50 minutes after the starting after starting the reaction, the profile of the UV visible spectrum is pretty much the same to that found after 1 day, after 24 hours. So the reaction can be considered conclude after just 50 minutes. What you have is the THF, but you have the sodium in the presence of crown ether. But you get a brown solution, and just by a slow diffusion of hexanes, you are able to produce crystals. And these crystals were determined by X-ray crystallography by Marina, is an excellent crystallographer. And as expected in the theoretical calculations, you see that the nanographenes like to intercalate the sodium cations inside. In this case, you have the anions, and you have this what is naked dianion, because the sodium cations are contained within the crown ethers. Okay, I will provide you now a different view, but in the solid state you can see that both the P and N isomers, because you have the racemic mixture. Remember that we have here an helicene structure, a helical structure. So you have both enantiomers, P and N, at the same crystal. And these in blue are the sodium cation, sorry, which are contained within the crown ethers. Okay, so in order to understand much better this reaction, because this is not a simple complexation reaction as I showed with you at the beginning. This is a properly redox reaction, which is quite unknown in these systems, in nanographenes. So it was carried out theoretical calculations, and you see that the first electrons given by the sodium atom form the radical anion species, and here you can see the spin density. But the spin density is mostly localized at the same position, the same carbon atoms where the LUMO is located, because the first electron, of course, is coming to the LUMO. Okay, so this is the radical anion, and this is followed by a second electron for the dianion species. Okay, these dianions, you can see that the second electron, if you compare with the starting neutral molecule, which is this is the nanographene 1, which is neutral, you see that mostly the electron density is mostly delocalized along the whole molecule. So this is what we observe, and Marina could follow this study by NMR. And look at this. This is the neutral molecule. So this is our molecule, the neutral molecule. You could see after the synthesis you have this spectrum. But once the sodium has been added and you form the dianion species, all the signals are significantly shifted. And this occurs 50 minutes after minus 80 degrees. Okay. What is remarkable here is that everything seems to be modified, but if you open your NMR tube, then an oxygen goes inside, the air goes inside, you recover your neutral molecule. So it's something which is remarkable is that these redox properties of nanographenes are quite reversible. That means that the systems are quite stable as well. But not only the influence is in the redox property, but the redox properties has also a strong impact on the aromaticity of the final molecule. These theoretical calculations were carried out by Professor Israel Fernandez at Complutense University in my department. And you can see that for instance, these are D and E rings are those where most the changes are more pronounced. So the change in aromaticity is mostly modified, which is always in the fusion in the borderline in between the curve and planar system. What is remarkable is that the NICs, the isotropic nuclear independent chemical shifts, where studies were calculated by Israel, and you can see that, for instance, the ring C, which corresponds to this one, is a negative value, which that means that the diatropic ring current, in other words, is aromatic. But the aromaticity can be decreased to non-aromatic or even anti-aromatic, like in this case, provided that the mix now is positive. Okay, so there is a dramatic change in the aromatic properties of this system by gaining 1 or 2 electrons, as could be expected. So let me tell you something in general on this family of compounds. And you see that this is 6, compound 8, 7 and 8 is pretty much the same. The only difference was the presence of the chlorine atom. So in some cases, I compare only 2 for the sake of simplicity. And hexa-benzocoronenes as a control, just to check. This in black corresponds to hexa-benzocoronenes, and you can see the absorption spectrum that eventually are just simply homo-LUMO transitions. The homo is mostly localized in the planar moiety, whereas the LUMO is delocalized along the structure, but with the larger coefficients in the place I showed you before. So in the fusion, in the borderline in between curvature and planarity. Okay, so basically this is the same for both compound 6 and 8. Okay, homo-LUMO transition. But if you have a look to the emission properties, this is quite different in the sense that you see that the molecule having the 7-member ring, compound number 8 or 7, with the 7-member ring provides you much more flexibility, has a kind of conformational freedom, and therefore it can be deactivated in a non-radiative manner. So actually this solder here could be considered a kind of, well, this is a dual, a dual, is another photophysical event, could be considered a dual emission or a bimodal emission. And this has been studied much more into detail. But just as a proof of this, the big difference here in between 6 with the helicene and 8 with the 7-member ring is that the fluorescent quantum yield here is roughly 50%, but here is decreased to the half, probably because this flexibility provides an alternative non-radiative pathway for the deactivation of the site state. The presence of a chlorine atom is 17%, probably due to the same effect as adding the heavy atom effect as well. So, without going into much detail, this is a very recent paper. It has been come out just a few days in Advanced Materials, where is the most serious, the most in-depth study on the photophysics of molecular nanographenes. And without I mention and go very much into detail, we could observe in compound 6 and 7, but 7 and 8 again is the same, pretty much the same. We observe not the fluorescence at very low temperatures. It's a little bit ring because of the frozen of state frozen in molecules. But we also observe the presence of phosphorescence at very low temperature. At 65 K, phosphorescence is also observed. Furthermore, it was also determined the presence of thermally activated delay fluorescence, the TADF, and this process occurs here in compound 6, but also here in compound 7 or 8. So in order to understand what is going on here, to give an explanation to this experimental observation, Professor Inés Corral from Autónoma University in Madrid, she carried out a beautiful study, a theoretical study, in which you can see that in the case of compound number 6, there is, the single site state, in which you have also a triple state, but in addition, there is another, it is called dark triple state, which is very close to the single site state. So this allows the energy difference, which is around 0.3 electron volts. That means that you can observe what it is called the reverse intersystem crossing. I mean, the electron from the triplet can go back to the single site state. And this is what we call the thermally activated delay fluorescence. So we need these small energy differences. But this was relatively simple because in this compound having the 7-member ring, it was much more difficult to explain because this is one of those systems in which you have a dual emission was observed here, and you can see that there is a single site state is almost degenerated. So you have a single site state A and another one B, which is populated from the excited state S5. So, but then in addition, you have the triple state, which is almost degenerated as well, A and B. But in addition, you need another triple state in close proximity to the single site state to undergo the thermally activated, the TADF, activated delay fluorescence. So as a whole, we can say that that the temperature decreases below, because this TADF is observed just in the range of 100 to 130 K. So below 100 K, the triplet manifold, all the states are stabilized, and therefore the distance, the energy with the single site state is too high, and therefore TADF disappear below 100. And on the contrary, at the temperature increase over 130 K, the triplet manifold becomes unstable, and not only the TADF, but also the phosphorescence disappear from the system. So this is the explanation. If you want to go much more into detail, this paper can provide very, very nice insights to people interested in. And the last part of my presentation is devoted to this family of bilayer nanographenes. Let me tell you that this is Professor Pablo Jarillo. He's an Spaniard working at the MIT, who published a Nature paper in 2018. And since then, he has published a series of Nature papers where he discovered this kind of, when you have two graphene layers and you rotate one over the other, like here, you can observe the formation of new superlattices. And this is what we call the moire patterns. And these, at the end, are superlattices with a new band structure and therefore modifying the electronic properties of the system. In particular, at 1.1 degrees at 1.7 K, it was determined that the bilayer nanographene exhibits superconductivity at this magic angle. In the next papers, it was reported that there are several values for these magic angles, and also not only bilayers, trilayers, etc. What I mean is that in graphene, pristine graphene, the properties of the bilayer are quite different to that of the monolayer. And just by chance, well, not by chance, but at the same time, it was another US postdoc student in Madrid, working in Madrid, just the other way around, and who was studying this system in our group. It was a paper published in the same year, 2018, in Endowed, and you can see that in this case, the quantum confinement of the electrons in these systems I mentioned you at the beginning is also able in the nanographenes to modify the properties. And that is the point I want to show you today. In this family of new nanographenes, which are called bilayer, helical bilayer nanographenes, the properties are quite different to that observed for the monolayer. And this is the message in the paper I will show you later on. And now the inspiration was to mix helicene with the nanographene. Okay, so the synthesis, nothing new. This was provided by Jean Crassou, this helicene, and we carried out the introduction of the substituents, 4+2 circular addition, short reaction, and we obtained the final compound in the racemic series. But starting with an antiomerically pure helicene, we obtained, as you can see here, M5, 92% in this reaction and 93% EE, the enantiomeric excess value is pretty much the same. In the starting material was 94. So the message, important message, is that along the reaction involving the short reaction under strong conditions, the enantiomeric information is retained. This picture is only to show you that this molecule is a molecule and therefore exhibit the typical features for studying and characterizing molecules. But if you have a look to the Raman spectrum that it is shown here, you see that it shows the D and G bands typical for graphenes. Now it's much more structured because of the loss of symmetry. But which is even remarkable is that you can observe even the overtones. So I mean these 2D bands which appear at these values. So the conclusion is that they are molecules, but the Raman nicely confirmed the nanographene nature for the molecule. Okay, so we are dealing with molecules, but at the end they exhibit properties like graphene. These are some of the properties: strong absorbance, bright emission, as expected. But we observe the evidence for aggregation, because when you increase from 10 to -5 to 10 to -4 the concentration, you observe the quenching of the emission at higher concentrations. And what is also remarkable is that if you take the enantiomerically pure, the enantioenriched material, M5 I mentioned before, you observe this designated signal with a positive and negative photon effect. But just by modifying, increasing the concentration, you observe that the transference of chirality through the molecule, and in the final ensemble, you have also chirality as a property. So again, here in these systems, Marina also carried out the studies, similar studies. So now I can go a little bit faster here. But now it's completely different because she did it with potassium and rubidium, and now it's not the dianion it was formed. Now it's a trianion. So in this case, this is the straight crystal structure, and it's not the same in both cases because the potassium are solvent separated from the rest of the make anion, which is formed the trianion here. But here the rubidium is different. One rubidium seems to be separated, but the other one are connected to the carbon layer. And this is what happened. Again, Israel Fernandez carried out this study, but now it's different. The first electron is coming to the LUMO as expected, forming the radical anion, and you can see the spin density. But now, instead of coming the second electron, hydrogen is transferred from the solvent to this species. And the result is what you observe here. If you pay attention, the aromaticity is lost, and a new methylene group, a carbon with two hydrogen atoms, is present. This is repeated again, second electron, radical anion, and again protonation. And as a result, you have just in the hexagon, in the first and sixth hexagon, so those hexagons belonging to the helicene moiety, which is the most strained part of the molecule, are responsible for this selective or site-specific reduction. This has never been reported in literature, and you can see that this is the first example in which a strain-induced reactivity in the helicene backbone is reported. So here you can see the CH2 group in the ring number 1, and also in the helicene. This is ring number 6, because the strain here is remarkably high. But in addition to this, the X-ray crystal structure is here, and you can see that it's not the same because in this case the potassium is free, but here perhaps you can see much better here. The rubidium atoms are, they are connected to the carbon atoms, forming this hapto-3 or eta-3 organometallic compound. So not only you have a selective, site-selective chemical reaction, hydrogenation, but also formation of new organometallic species, which are less known for these materials. And just my last minutes are dedicated to this family. When we published this Angewandte in 2018, we said we are reporting a new family of synthetic double-layer nanoforms of carbon. Further work to control the geometric relationship between the layers and explore the intercalation metal is underway. The intercalation metal has been already provided, so we made our commitments. And the second one is this paper, the last one I will tell you today, because just by modifying the length of the helicene, this was reported, the paper reported in 2018 with 10 helicene. So now we have 11 helicene and 9 helicene. This is in going from 11, 10, and 9, the overlapping in between the layers is significantly increased. And this is critical for the paper I will show you right now. Well, the synthesis is here. Irena Stara is acting in this event. She provided us with these beautiful cases with chemically modified helicenes. And then it was we were able to obtain the final compounds here. And also Professor Jan Krasuk provided the measurements of the optical properties, in particular cross-polar luminescence. This is to prove this. Of course, here is without the tertiary group for solubility, but you can see here these are X-ray crystal structures, and you see that in this upper view, the zenithal view, that the overlapping of the two layers is tremendous. Here in the 9 helicene, here is partial, and here is almost nothing. The only overlapping is occurring in the helicene moiety. Okay, and different crystallography, different crystal package. And the most significant result came from cyclovoltammetry, because we determined the redox properties, and you can see in these 3 systems that the first oxidation potential is occurring here at these values. It's quite remarkable to see that this molecule exhibit, in this case, for instance, the reduction potential is 0.4 volts, much more electron donor than hexa-benzocoronenes. So something really extraordinary is happening here. These are powerful electron donor systems. Here are a little bit less, but this is related with the pi-pi overlapping. And here is probably because the formation of the radical cation can be delocalized as a kind of mixed valent compounds in between the layers, which is significant and quite new. So the properties is significantly, this you can compare because the larger conjugation increases in going to the 11 helicene. However, the donor character is increased with this one. In principle, this is significantly different to that expected, because according to the extension of the pi conjugation, this should be the stronger donor, but now a different effect is occurring. As expected, because the helicene moiety is almost not affected or very poorly affected, the reduction value is pretty much the same in all cases. So this was fantastic results obtained here. And just here is the absorption, but again, the emission spectrum, as I showed you before in the previous example. And look at this, compound 9 is significantly, well, first of all, let me tell you, this very broad emission is a typical signature for the formation of heximer type emission. So the formation of heximers is probably occurring here. But what is much more shifted is that where the pi extension is lower, which is compound the 9 helicene. You can see here the big difference in between them, 9, 10, and 11. So this is interesting because the probably better emission and quantum yield in these cases, okay, in particular for this molecule. So let me go to the chiroptical properties because photoluminescence has been already mentioned. But here you can see the after separating by chiral HPLC, both enantiomers and MP, you get you go to the dichroic signals. I mean to the circular dichroic spectrum, and they are pretty very nice mirror images in all cases. So both enantiomers were separated, and in this case the circularly polarized luminescence, which was measured in this equipment, was determined. What is remarkable again is that the molecules should be expected quite similar, but if you pay attention to the dissymmetric factor, in this case is or the Jellum value is in this case is 3.6 10 to minus 2 for this compound. This is the bilayer with the 5 helicene. The 5 helicene in the final molecule is transformed in the 9 helicene. Okay, it increased 2 benzene rings in each layer. So this is fantastic value. This is one of the largest value reported for a carbon compound in the literature. And these are theoretical calculations were carried out by Juan Casado in Malaga, and they pretty much are matching with the experimental results. This is the expression for determining the dissymmetric factor is depending, of course, the electric and magnetic transition dipole moments, which are shown here, and also the angle in between them. So probably this orientation is much more favorable than the other one. So the properties again are changing. And well, let me bring to your attention this paper was come out just a couple of years ago, where they propose, they are experts in this topic, and they propose consider not the dissymmetric factor, the Jellum value, but what they call the brightness. And the brightness, in addition to the dissymmetric factor, it also considers the absorption and the quantum yield of your molecule. So at the end, what the brightness provides you, in our case, this is the brightness, because you can have a Jellum value very high, but if the absorption is very low or the quantum yield is very low, the final your material would be not useful for this purpose, because this value, the brightness, provide you the total amount of circularly polarized photons which are emitted by the compound. So look at here the tremendous difference of the pi overlapping. In our case, resulted to be significantly larger than those obtained for the 10 and 11. So this is, as mentioned you before, is one of the highest values reported for a compound constituted exclusively by carbon atoms. Okay, so these are the conclusions in this part, that the overlapping this provides you the helicene length determines the pi overlapping in between the systems, and this determines in turn not only the photoluminescent properties but also the dioptical properties. And this is something similar to the works by Pablo Jarillo. The magic angle effect is a kind of resonant condition where it is as easy for the electrons to go through one graphene layer as it is for them to tunnel to the other graphene layers. In other words, the two layers are in electronic communication, similarly to our molecular system. So these are the conclusions. So let me go to the final conclusions of my presentation. It is the rational design allows to obtain chiral nanographene at will, okay, as a dimension of control. Size and shape are of interest for preparing supramolecular ensembles, forming all carbon compounds. These nanographenes undergo interesting reversible redox reactions with alkaline metals, and the formation of new organometallics has been reported. Also, the richness of photophysics in these systems is still to explore, but please pay attention to this advanced material paper has been come out just a few days ago. And finally, to conclude, the outstanding CPL values and the brightness in our systems are quite relevant, are among the highest reported as well in the literature. If I have 2 minutes, exactly 2 minutes, and let me tell you that this project, the Kintronic, together with David Ecija from India Nanoscience and Pavel Jelinek from Czech Academy of Sciences and the Institute of Physics, by using this equipment, this is the new flask to carry out chemical reactions. Okay, but this provides you some limitation associated with the synthetic wet chemistry. So with this in mind, we have a new scenario to test new reaction and get new opportunities. And this is the reaction we studied. This is a new reaction unknown in chemistry and unknown in the chemistry on surface. So this is a brand new reaction where basically it was the first paper was come out in Androvanti 2019. And you can see that the bromination of these tetrabromopaраquinodimethanes, these are the reactive groups, just by increasing the temperature from room temperature. This is a gold sulfate, to 400 K. You see different steps, debromination, formation of this intermediate vinyl carbenes, probably, and they are forming the oligomers and eventually the polymers. By acting in this way, and this is my last slide, with anthracene, we were able to obtain these pi-conjugated polymers. You can see a brightness here. You can see that when we use pentacene, is different. So we get the polymer, but there is no dish protrusion. So different behavior. This is aromatic alkyne. This is paraquinoid cumulin. This has been extended to Byzantine. And look at the beautiful nanographenes are obtained and characterized, electronically characterized with a pentylene. This is anti-aromatic unit. So we are combining aromaticity and anti-aromaticity in the same systems. We have used pentacene by radical polymers. So you are able to obtain open cell systems like this one, or play, for instance, with this paper that depending on the length, you can get trivial or non-trivial topology that this open a new scenario for this system. So this is, let me thank you for this couple of extra minutes, but this is the research group. Here are the collaborations. Mostly these are current collaborations and mostly engaged with this topic. And in the group, all the people you can see here are in some way or the other, they are related with nanographenes, and the people with the arrow over their heads are those who has been directly related with the presentation I have made today. So thank you very much to all of you for your kind attention, and also for being able to understand this lecture of around 1 hour. Thank you very much.
Thank you very much, Professor Martín, for the amazing lecture showing us how, starting from a simple benzene ring, one can get highly complex structures with chirality, with unique optical properties, and making this nanostructure highly functional. Now, let me introduce the people that are with us today. So we have two panelist members and one challenger. The two panelist members, first of all, we have Irena Stara. Irena Stara is a senior scientist and project leader in the group of chemistry of functional molecules at the Institute of Organic Chemistry and Biochemistry of the Czech Academy of Science in Prague. She is a member of the editorial board of Journal Physical Organic Chemistry and member of the International Advisory Board of the International Symposium of Novel Aromatic Systems. She serves as the chair of the board of trustees of the Experientia Foundation, the biggest private foundation supporting science in Czech Republic. She published nearly 100 papers in the 6th chapter in books, and she was actually received the honor of becoming Chevalier de l'Ordre des Palmes Académiques by the French Ministry of National Education and Youthness. And so that's the first of our panelists. The second of our panelists is actually Junzi Liu, that is currently assistant professor in the Department of Chemistry at the University of Hong Kong. His current scientific interests include bottom-up organic synthesis of topological nanocarbons and their application in organic electronics. Is particularly interested in nanocarbons with alternated topologies, atomically precise synthesis of 3D nanocarbons, and supramolecular chemistry. So Dr. Liu received this bachelor and degree in materials chemistry in 2008 and a master's degree in materials science 2011. Then she joined the Max Planck Institute for Polymer Research, where he carried out his PhD thesis and obtained his PhD in synthetic chemistry in 2016. Then he stayed at Technical University of Dresden as a postdoctoral fellow, and later as a research group leader and chair of the chair of molecular functional materials in TU Dresden. And then in 2019, he moved to the University of Hong Kong at the Department of Chemistry. He already received quite a few awards, for example, the Small Rising Star Award from YDVCH in 2022, the Emerging Investigator Award from RSC, CENCOM in 2022, the NSF-C Excellent Young Scientist Award in 2021, and so on and so forth. So I will not lose much time because it's good that we give some time for them also to pose questions. The last person in the team that is our X-Challenger is actually Shuting Dai, that is a PhD candidate majoring in physical chemistry at Jinling University, supervised by Professor Bin Xu. She received a Bachelor of Engineering degree from the Dalian University of Technology in 2019, and presently she is at the University of Strasbourg in a joint PhD program focusing on novel van der Waals heterostructure based on organic and inorganic 2D materials. So now let's start actually from the challenger. Let's start from Shuting, and who is ready to ask questions to our speaker. Please, Shuting.
Okay, thanks for Professor Summary for the introduction. That's a wonderful talk, and Professor Martin shared a lot about the synthesis and the properties of nanographene. Here, I have two questions. And the first question is, if we try to apply external forces onto the helical bilayer nanographene, such as the shearing force or the high pressure, do you think it is possible to adjust the sleep distance and the overlapping area, so as to realize the manipulation of the physical and chemical properties?
Yeah, the question is very good indeed, because actually this is a project that has been open, has been discussed with some people who is expert in applying pressure by using the diamond and so on. But still, we don't have results so far, because even though the required amount is very small, in the collaborations it takes a time. But this is certainly one of the things has been considered for doing. And the contact has been established. Let me tell you, by the way, that it should be expected important changes, because these molecules are relatively not flexible, but they will respond to the if you apply a pressure, for sure. Actually, just when in these systems going to those Marina Petruchina systems, when you have a curvature or something like that, and you modify the electronic properties, you observe that the planarization or increase of curvature depends on the system. But for sure that the geometry of the molecule, just answering to your question, will respond to the effect of the pressure. That would be something we would like to know, specifically in this molecule, because it's very, very appropriate for this study. Thank you for the question. Yeah.
Okay. Thanks for your detailed answers. And the second question is, I see that you introduced many kind of nanographenes. And do you think what kind of structure of the nanographene would be easier to combine with the fluorine to form a super molecular complex?
Yeah, of course that the only limit here is the imagination of the researcher. You know what I mean? Is that in principle, well, when we started studying the first complex I saw with you that was carried out by Chus Fernandez in our group, we didn't know exactly how the result would be. But at the end, you see that the concave-convex interaction, that is something we have studied extensively in our group. It makes a sense. So regardless of the binding constant, I like to say that sometimes what is not happening in the ground state happen in the excited state. So sometimes you can see the binding constant relatively weak, but if you use photoinduced electron transfer by using lasers or the appropriate energy, you can observe the transfer of electrons. So it could be of interest to study these systems. In principle, there is no limit. There is no limitations to the shape, because sometimes you feel sometimes the curvature provide good opportunities, but also planar systems are well depend. You can get important binding constants as well. So I wouldn't say that there is not a rule. So any molecule having a surface where can interact, because sometimes you are looking for pi-pi interaction, but sometimes could be other. As I mentioned you, if you decompose this interaction, it can be a surprise to see that any other interaction, electrostatic interactions or whatever, can play a role. So in principle, well, it makes sense. Just consider those molecules that can fit, and that would be enough.
Okay, thank you for your answer and your wonderful talk again.
Thank you for your questions. Thank you.
Thank you, Shutin. Now it's time for Irena to pose any question that she might have.
Well, thanks. Irena knows.
First of all, I would like to congratulate Professor Martin for really excellent talk, and I really like it. And I also would like just to thank for inviting me to this very interesting discussion. Well, my question would be such: for different properties, it is really essential to introduce a defect into the structure. And it is very frequently done by introducing heteroatoms. And my question is, if you consider to have a heteroatom into hexa-benzocoronene core, or perhaps you try it already?
Yeah, interesting question, because I guess that the step after the pure carbon chemistry, nanographenes, is already there are some groups that are performing wonderful research introducing heteroatoms, not only nitrogen, that could be expected in principle, but other heteroatoms, boron, even boron and nitrogen, and also phosphorus as well. So this is a possibility. In principle, for instance, and you know pretty well this story, but introducing heteroatoms in the helicene moiety is also another appealing possibility. So yeah, it is true. Your question is appropriate. We are not now considering specifically for a medium or short time to do it, because you cannot do everything. But in principle, that would be the next step for sure. Actually, let me tell you that without looking for that, we got just by chance an helicene having a sulfur atom. I said an sulfur, an oxygen atom inside, you know. So even if you are not looking for them, they come to you. So heteroatoms are present. So that will happen very soon, I guess.
If I may have a second question.
Sure.
Just, I am curious because if you try, or if you consider just to make a self-assembly from the bilayer graphene on the surface to form the monolayer, with the aim to study charge transfer or transport, and to study cis effect, as it was described by Ron Naumann. As you know, cis effect is just chirality induced spin selectivity, which concerns the phenomena that if we have a chiral environment and electrode penetrates through it, spin polarization appears. And I think it would be quite interesting to study in your system. What's your opinion?
Yeah, completely agree. Actually, we provided a sample of these materials to a group who is working on depositing this material on surfaces. It's not a group we are currently working with, but all these, this is one possibility. I don't know how the result will be. Is under studies currently. But I cannot tell you honestly, because we don't have results yet. At the beginning, it was difficult to handle, but eventually seems to be something reasonable will start to appear over there. But yeah, to play with chirality, as you mentioned at the end of your question, is an added value. So what you get at the end, it is true that when you put something in a short phase and you want to carry out on-surface synthesis, at the end, you are going to get probably a flat molecule, you know, and in this case, chirality, which is performed with a helicene or so, could be lost. But of course, you have a planar chirality that is still surviving over there. But my feeling is that these systems could be much more of interest for acting like spin filters or any other materials from this viewpoint, rather than deposited on well, unless I thought you was referring to make a synthesis with them, but if they are organizing on surfaces, I fully agree with you.
Mm-hmm. And perhaps last, very short and very provocative question: what about to have triple layer systems?
Very soon.
Okay, good. Thank you.
That is the only thing I can say. Very soon. We can very soon. This is like a chapter in the TV.
Okay, good. Thank you.
Okay, hopefully.
Yes.
We
Good
have
luck.
a talented synthetic guy in our group. This is Salvatore and Sergio.
It's very nice.
Hopefully very soon.
Thank you.
Thank you. Thank you for your questions, Irena.
Excellent. Thank you, Irena.
Paulo.
That's great to hear also what is going to be next on the under the hood in Madrid. No, let's go. Yes.
Paulo, your voice was not continued. Okay.
Okay.
I think it's from your earphone. Okay. Yeah, Junzhi, please.
Yeah, yes. Professor Martin, thank you. Very nice talk and also inspired.
Okay.
And actually, I learned a lot from your work. I'm actually closely follow up your work, especially related your GX paper. Actually, I have one question, right? By increasing the overlap, such as G value or brightness, could be improved a lot. So I'm wondering whether we can, or not us, whether you can control the distance of the bilayers instead of the overlapping, because by increasing overlapping, the G value and the brightness could be improved. I'm thinking about whether you can control the distance of this kind of bilayer to say whether the distance can affect the purpose of G value or brightness. Yes, or did you try it?
No.
Or have you tried already?
No,
Thank you.
certainly you are completely right, because now it's time for playing with the interlayer distance. And if you pay attention, if you remember at the beginning when I showed you this beautiful picture with these molecules flying over there, at the end I mentioned another bilayer. The shape was this shape with a completely control on the 5 stereogenic elements contained. So this molecule has. May I go to my presentation, because I think it's worth it to have a look.
Yes, please. You can share it,
Yeah.
Professor Martin.
Yeah. So let me go. Yeah. I cannot move it. So okay, okay. Anyway, I cannot. It's out. Okay, now. Okay, now it's. Let me check it first. Yeah. Yeah. Now it's perfect. Let me go very quickly. Just at the very beginning of my presentation, you can see here. This is. I don't know if you could see. Could you see this?
Oh, sorry, we couldn't see it. Yeah.
Okay, then let me share the screen. So, okay.
So,
anyway, no. Okay, sorry for that. But anyway, what I mean is that in this molecule, that we have different chiral. Not only the distance is quite different, because now instead of having because in the bilayer family is typically the graphite is roughly 3.4, 3.5 Armstrong. But in the molecule I show with you, this is almost 1 nanometer. But now, of course, that you are losing the the connectivity, the interaction. They are not pi-pi interacting, and therefore, for instance, if you have a look to the oxidation potential, it's pretty much the same to the hexa-benzocoronenes. Not like happened in the other case that it was significantly. So the properties are strongly modified. However, this is much better to introduce something inside, maybe even with a strong chiral environment, you know. So you can play with all these systems. And what is relevant, and I would like to communicate to the chemical community, is that hopefully very soon we also will come out the first nanographene in which has been obtained in an antimerically pure form without using HPLC separation. And this is with EE values surpassing 97%. This is tremendous. This is the power of the organic synthesis, and this is as synthetic chemists what we must do. Not only this will open new scenarios. So this is one message to take home. Okay.
Yeah. I have a second question. May I? Yeah.
Sure.
And beyond the science, I have one general question, especially for a junior faculty. Maybe many of people like me sit in front of the screen. So at the beginning, such as for our independent research, because for your first slides, you have showed different maybe 9 figure or topical. So at the beginning, do you have any suggestion for the junior research how to start the research topical or whatever? So do you have any suggestion or comments for that? Especially for me, I have met this kind of challenge. I'm always thinking about how to continue my work. Yeah.
Well, well, it's difficult to give an advice, but my advice is always enjoy science. Enjoy science, because if you enjoy, you are able to do anything you like. And now we are current times are very dangerous, particularly for young people. Be careful with the predator journals. Be careful with many aspects that at the end can damage the future of young scientists. So first, science appears just to satisfy the curiosity of the human being. And also in the second step is only just to understand our world, And the third derivative, the second derivative would be just to improve the quality of life in our planet. Don't forget this element. This is what is critical. In future, only those people doing science just for the sake of accumulate papers and more papers and so on, so would be useless. And my feeling is that in most advanced countries, people are paying a lot of attention on this aspect. So my comment for young scientists is go to something that you consider is important. Try to solve problems and then publish in the most honest manner. Okay? Don't try to multiply your papers by 3 just by fragmenting or whatever. But essentially, enjoy science, because I enjoy science all my life, and that is the reason, because I don't care if I'm working 10 hours, 2 hours in a day or not, because you are doing what you like to do. So that would be my advice for any young scientist. Okay.
That's cool. Yeah. Totally agree.
Okay.
Thank you. Perfect. Thank you very much.
Thank you very much to the panelist member, to the challenger, to Professor Martin, who gave an amazing talk and also gave very important tips for what to focus in science and how science can be important for the society. That, I think, are really the take-home messages of today. There are quite plenty of them to go on with. And now I like to stress that this series will continue after the amazing lecture of today. We will go next week, actually. Next week, we will have another lecture on another way to look at layered structure. That would be more from the physics point of view. would be layered material characterization application given by Professor Andrea Ferrari from the University of Cambridge. And we have also distinguished a list of people that will participate to this event with Alice Zhang, with Julia Chang, and actually Martin Duo will be our moderator. So with this, I like to warmly thank all of you for having passed the beginning of the afternoon here in Europe or other part of the day in the rest of the world with us. And remember that iCANX talks are there to connect the world and universe. Is the best example of open science and to share knowledge and to share the let's say best result in science with the rest of the world. So with this, I'd like to thank again also Alice Zhang again for setting up all this amazing series of lecture. And I wish you a great day and looking forward to meet all of you next week.
Thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。